Okay, so this example is for my 8th period class because we didn't get quite as far. And 7th bell, if you see the link and you're working on it, you can also use this as a way to refresh kind of what we're doing. This is just a second example where we are going to take a shape that's not as basic as one of our simple three, rectangle, triangle, or semicircle. It's the combination of a couple. And we're going to break it, basically identify the two regions, the two shapes to deal with, and then how do we do what's called like a weighted average of those regions to kind of find the centroid of the region that we have here. So first off, I think you can see that we have should be a right triangle. Okay, so I'll call the triangle region 1, and then I will call this semicircle region 2. Now what's different is that the semicircle is a cutaway, and we didn't do that yesterday in class. That's why I wanted to have you see another example. So we're going to isolate and just focus on one shape at a time though. So I'm going to make my kind of little table over here. I've got shape 1, and then I've got shape 2. And what we want to find out about each shape is we want the coordinates of the centroid of that shape. So we're doing the x bar and the y bar to represent the x coordinate of the centroid. Now as we list out coordinates, they need to be within reference to the same origin. So I need to define a point to be 0, 0. And I'm just going to make this corner right here. Let's just make that point be our 0, 0. Okay? I get to pick that. As long as I'm consistent as I mark out points from the same coordinate, then I'm okay. Alright, so to find for region 1 is the right triangle. We're going to ignore that and just focus on only the triangle. To find the centroid of a right triangle, from the right angle, you go 1/3 of the length along each leg. So this leg is 30 units long, so 1/3 of 30 is 10. So I would come over this way 10 units, okay, and that's 13. So I'm approximating 10, and then we would go vertically 1/3 of the way up this, and if that's 24, then 1/3 is 8. So I'm just kind of annotating, you know, maybe it's going to be like right in here. Okay, and that would be at the coordinate over 10 up 8 from the origin. Okay. The second shape is a semicircle. And to find the centroid of a semicircle, I can make a little side note. We know that the center of mass of a semicircle is going to be in line with the center here of the arc, okay, along that diameter. But the question was really how far off of that. It's going to be somewhere along this line, but how far away? Well, the distance here, there's a formula, is 4 times the radius divided by the product of 3 and pi. And the radius is given to you as 5. So if I use that value, it's 4 times 5, or 20, divided by 3 pi. So what's 20 divided by 3 pi? Now on your calculators, make sure you divide by the product of 3 pi. So I've got a calculator pulled up, so I'm going to type in 20 divided by, I'm going to do parentheses around 3, and get the second wrong button there, pi. Okay, so that I'm dividing by the product. If I just hit divide by 3 and then hit times pi, it's as if the pi is in the numerator with the 20, and I'll get the wrong answer. So this is a dimension here, distance, vertical in our case, of 2 point, I'm just going to round it to the nearest hundredth, 1, 2. Okay, so I'm over 13 units and up from that origin right here. So if I think of where is that centroid, I'm over 13 and up 2.12. Okay. The next thing I need to find is the area of each region. Okay. To calculate the area of a triangle, it is 1/2 times the base times the height. And it's a right triangle, so the 30 is the base, the 24 is the height, so I'm just going to do half of, I don't know if you need to see some of this scratch work, but half times base times height is the area of a triangle. So that's half times 30 times 24. So that's 15 times 24. What is 15 times 24? It is 360. So I've got an area in region 1 of 360 square units. Okay, the semicircle, well, a circle is pi r squared, but we want half of it. And so our radius was 5, so it's pi times 5 squared, or 25, right? Divide by 2. Now, we're going to have to do something different, though. Let me hit 25 pi is that, divide by 2. So as a quantity, it is 39.27. I'm going to round again just to the nearest hundredth. But when I put it in the table, this is where I have to acknowledge that this shape, I've kind of taken a big region. Really, the material that I'm trying to find the centroid of is this. And the semicircle is not part of that region. It is a cutaway. It has been removed from a shape. And so if I'm trying to account for it as not part of the mass, the area in question is a negative area. It is subtractive. So I need to have a negative 39.27 area. Okay, so now I have the coordinates of two different centroids, and I have the areas that they represent. One is positive, and one is negative. Okay, the formulas that we're using, let's write the formula. So the x bar, this is the centroid of the complex shape, is equivalent to the summation. So finding the sum of all the instances of this expression, and that is, okay, the centroid's x-coordinate times the area of the region. I think of I as standing for each instance, or in our case, each region or each shape. They don't know how many shapes we're going to break our complex shape into, so they just use generically I. And so we have to find the sum of basically this expression, however many times you can figure it out. And this is a product of two things. So we have to find the product, and then you have to find the product again for shape 1, shape 2, etc. for each instance. And then we're going to divide by the sum of the areas of all the shapes. Okay, so I need to find the product. Oh, I'm kind of off the screen, aren't I? Sorry. I need to find the sum of the product of the x-coordinate of the region, so of the first shape, and the area of that region. Okay, so right here I have the x-coordinate of shape 1, and I have the area of shape 1. And so I'm going to list that this is this expression. It is multiplying the x-coordinate times the area. So 10 times 360 is 3,600. And then 13 times this would be the other one. So I'm going to use my calculator here, and I'm going to use a negative. Oh, can insert the negative. So negative in answer, it'll copy that exact value, times 13. So I have negative 510 point, I'll go 51. So negative 510.51. Now, to get the x-coordinate of the centroid of the final region, I need the sum of all of these. Well, I only had two shapes, so I only have two instances. So I have two of these, but I'm going to find the sum of those. So my negative 510, I need that plus the 3,600, and I get 3,089.49. That will get divided by the sum of all the areas. So right here, I've got the areas of the shapes. I'm going to add those up. So the 360 plus a negative is minus my 39.27, and that's 320.73. So this is going to be the 3089.49 divided by the 320.73. So 3089.49 divided by second answer. I don't have that answer gets copied down, the previous answer. Hit enter, and it is 9.63. And let's go ahead and complete it for the y's, and then we'll kind of summarize and talk about these numbers. So to repeat this process for the y, the formula looks the same. It's the sum of, for all the shapes for each instance, the y-coordinate of the centroid times the area. Okay, and then we're going to divide by the sum of the areas again. This is basically doing a weighted average. We had multiple centroids, and we don't want to just average them because this centroid represents a large area. This centroid actually represents the removal of material. But the amount of removal, or the amount of area that this represents, is not as big as that one, so they shouldn't have equal weight. So we don't just do a straight average, just average the x-coordinates, average the y's, because we'd always be kind of right in the middle, but that's not what happens. Our centroid shouldn't be here. Okay, so we'll come back and talk about that. But so like I said, we'll finish this off. So I need the product of the y-coordinate and the area this time. So the y-coordinate and the area, and this will create another column. And then I'm also going to sum. We only have two shapes, so we only have two times to figure out each thing, and then we find basically the sums. All right, so I need the 8 times the 3600. So 8, or no, sorry, times the 360. 8 times 360. Yeah, be careful you don't, grab these. So it's the y-coordinate times the area. 8 times 360 is 2,880. And then I need this y-coordinate, 2.12, times the negative area. So 2.12 times the negative 39.27. Now I do have on my calculator a negative button. I didn't hit minus because I think that'll mess me up. So this 2.12 times the negative 39, and that was negative 83.25. So that answer plus, I'm going to now find the sum. Okay, the summation of this expression, the sum of that is just adding these two together. So the sum of each instance of this expression, I only have two instances. One's for shape 1, one for shape 2. So that negative 83 is my previous answer plus the 2880, and I get 2796.75. Okay, so 2796.75 divided by, still have the same area, total area of 320.73. So that divided by 320.73. And I get 8.72. So that is my coordinate, 9.63 and 8.72. That is the location of the center of mass. So if I wanted to be able to put the tip of a pen, if I were to cut that out and I wanted to be able to balance that shape on the tip of a pen, this is where I would go relative to this origin. So that was over 13. So this was 10, remember, okay, the centroid. If you use that as kind of a reference point, that was 10. I'm not quite as far as 10, so I've skewed that original centroid to the left a little bit. And the 8.72, well, remember that was at a height of 8, so that one's skewed up. So I am just illustrating, I am left and up of the triangle's centroid. Now, does that make sense? I think it does. Okay, if you imagine trying to balance something, right? If we had the middle and it's balanced, okay, we're good. But what if it's not balanced? What if this side is heavier and it's teetering like this? What would you do with this point to try to balance it? Well, the part that's tipping down, right, it's heavier and this is lighter. In order to get it balanced, we need this side to be heavier. How do we get it heavier? We could shift our point, so if we slide this way, there's now more mass here and less mass here, and this gets heavier, and hopefully we've been able to balance it out. So I'm shifting towards the heavier side to get it to balance. Well, why is that the case that this was left and up? Well, if you think of, if we didn't have this cutout, this would be the centroid. We'd just have a simple right triangle. But when they removed this from the triangle, we removed mass, okay? If you think of thinking vertically and horizontally, okay? So first we'll kind of think with this vertical line. A vertical line would kind of break the shape into two sides, the right side and the left side. Okay, more of this right? We've removed material. We've removed more from the right side than from the left side. So the right side got lighter and the left side is heavier. So what do? We shift into the heavier area, removing some mass and shifting some of the mass to the other side, right? So a shift to the left made sense. Now if you think of a horizontal line breaking into a top and a bottom area, we have in essence this cutaway removes mass only from the bottom. So the bottom got lighter and the top is now heavier. So we need more mass here on the bottom half. So we shift up, right? So now this new line, right, we have more mass added into the bottom half than the top half. So shifting that. So that completely makes sense. This cutaway being kind of to the right, if you think of the quadrants, in the right lower quadrant, we're removing material. We need to shift left and up to compensate. Okay? So, big picture, it makes sense where our centroid was, and just identifying the process again and kind of how this makes sense with our formula. Okay, we take our complex shape and we break it into regions. So we have big region being the triangle, and the second region being this semicircle, which happens to be a cutaway. Okay, so that's why we have a negative area, and the triangle is representing mass, a positive area. We find the centroid of each shape. So ignore the cutaways or whatever, we're just, if they fall within the big region, we're just focusing on a triangle. So shape 1, triangle, has its centroid. Triangles, remember, you go a third along each leg, okay, when you have a right triangle. So a third of the 30, a third of the 24. We get the coordinates from an origin. Shape 2 is the semicircle, okay, so it is in line here. This was 13 to the center. We know we're going to be along that line, so we were 13 over, but it's how far up, and that's where we use this 4r over 3 pi formula. So that's the distance you come off of the center mark of the arc. So 4r over 3 pi we did, and we got the 2.12, how far up. All right. Then we calculate the areas of our regions. So triangle is half times base times height. 30 is the base, 24 is the height. A semicircle is half of a circle, so a circle is pi r squared and half of it. Because it's a cutaway, it's a negative area. And now this formula says to divide, right? What is a fraction? It is division. So it says divide the sum of this product. So however many times for every instance you can create that product, go add all of those products. Well, how many instances you have is how many shapes we broke this into. So we only had 2 shapes. So we can get this product twice. We get it for shape 1, we get it for shape 2. So it's the x-coordinate times the area, right here. So that we did for shape 1, these 2 here, these 2 here. We add those together, that is finding the sum. So this is the sum, this 38.9 is the sum of that product for each instance. Then we're going to divide that 38.9 by the sum of the areas, so basically the total area. And the total area is actually the area of the material. Okay, so our cutaways should be negatives, so we're taking a subtractive approach to finding the total area. We divide those and we get the coordinate of the, in this case that was the x. Then we do the y's, so we need the y coordinate times the area to get these, and we repeat the same process. And there you go. I had another example. I could do another one. I did another one in class because we had time in 7th Bell, but it's very much the same. I had a rectangle with also a semicircle cut out. Honestly, it's not going to look much different. So I'll probably leave it at that. You can always kind of hit rewind, pause, go backwards, etc. to look at this. I guess I can leave you with this though. Your shape, so the paper that you would get to try in class, is going to be more complicated. It's going to have more shapes, and I'm not going to draw it. At least I don't think I'm going to. feel like I'm drawing like a plane or something. Okay, so let me just take a shape that I feel like by drawing I can break it into rectangles, triangles, and semicircles. And we want to do this in as few of shapes as possible as well. The one that you're getting on paper actually breaks into 5 shapes, so try to figure out those 5. So here I think I'm seeing that if I were to drop a vertical line right here, I clearly get a right triangle. So how about we call that shape 1 maybe. And if I go this way, I have a rectangle, that would be my shape 2. I have this triangle that got created, which could be shape 3, and then I have this, which is shape 4, the cutout. So I have 4 shapes. I'm not trying to break little shapes here, right? I'm taking a subtractive approach. So I have a positive, a positive, a positive, and a negative when you think of areas. So I'll have 3 positive regions and 1 negative region. But I'm just going to have, when I do my chart, I'm going to have 4 rows of listing out x and y coordinates of centroids. Okay, and then I'll have 4 areas, right? And then this we're not going to need. It's your sum's going to be here. So if you think of getting yourself organized into a chart, you'll then have for each instance, you'll multiply the x coordinate by the area, and you'll multiply the y coordinate of each centroid by the area. Okay, here's all your sums. Okay, getting the final x coordinate will be, if I labeled these boxes, box A, B, and C, and if you understand that this is just the totals down here, right? The formula, that fancy formula, is really box B divided by box A. And then the y coordinate of your centroid is really box C divided by box A. Okay? So that is that fancy formula, the sum of the products of the x coordinates in the areas divided by the sum of the areas. And this really is like doing a weighted average. If you've ever had a teacher that has calculated your grades using a weighted average, we're basically going in here and we're finding centroids, right? So if you kind of drew centroids, there's going to be a centroid here and here. You got 4 centroids, right? Well, we've got to average them together. But if we did a straight average, that would mean they all have equal weights, but they don't represent equal areas. This one, region 1 is this triangle, and that triangle is not as big as this rectangle. And so that rectangle is a bigger area. That centroid should carry more weight than that one. So if I was if it was just a trapezoid, kind of like that, we wouldn't expect those centroids to be, dead middle. We'd expect it to be closer to this one than this one. This one's carrying more weight. Okay? So that's why we're using the area in the formula, and that factors in, because we have to do a weighted average. All right? And then this one, right, well, it's actually has kind of a negative effect. This is not material. This is the removal of a material. So we've got to have, what did I number that one for? So you got to remember to have a negative area if it's a cutaway, if it's not part of your material. So the actual material that we're trying to find the centroid of, if I draw in section lines, is that. Okay? I hope that helps. I hope that sets you up. You're going to have a chart that looks like this, right? Find your coordinates, calculate the areas, and then you're multiplying, right? These 2 products get that column. These 2 multiply to get that column. I don't know if you can tell the difference between purple and blue on the video, but okay, those 2 are going here. These 2 are going here. Then you can total everything up, and like I said, B divided by A and C divided by A will give you your final answer. So good luck with that. Please persist, persevere, use the video, don't give up, you can do it. I'm here with you in spirit. I've got the video. I really think you can get this, guys.